All right, well, we've made it to the third module of Bootcamp 1. The third module is Basic Plotting and Statistics in R. You can find it here. So we're going to go through some basic data visualization and statistics because we have basically made it through the initial stages of a standard data analysis workflow. What we've done is loaded data, we've checked data, we've run various summaries, we've made sure that we've manipulated anything, we've dealt with missing data. We've basically gotten to the point where we're ready to do stuff with our data. We're ready to really do some visualizations, we're ready to do some stats, and to get some results. And so let's get to it. So the first thing, as in any module in this R Bootcamp, first load the script, download the script into your working directory. I'm going to save this into my working directory, R Bootcamp, and just save it in there. It should be a .r file already. And let's go into RStudio and load that script up using the file icon up here and finding the Bootcamp, finding the module that we want to work with, which is module 1_3. So you should have a script that looks something like this with a bunch of comments at the top. And we're going to start working with visualizing data. R is a great tool for data visualization in addition to data analysis. Those of you who have worked with SAS in the past for data analysis will know that not all data analysis tools are great for data visualization. SAS is a great example of that. It's not very good for visualization. Researchers typically use other tools for data visualization because SAS is not good at that. But R really does everything well. R is very good at you can make plots that are publication quality without too much trouble entirely in R, which is pretty cool. All right, let's get started. We're gonna, to be able to visualize data, we need some data to visualize, and we're gonna use one of the built-in data sets, which is the trees data set. We've already seen that in our Whirlwind overview at the very beginning. If you want to learn more about the trees data set, just do !trees, and you can find that we have 31 felled black cherry trees that are in this data set. That is 31 rows, and each of those trees was measured in various ways. We have girth, height, and volume, and each of those is associated with a particular unit, so we can learn more about that, and even a paper we can refer to. Let's look into that data set. If we want to see the data set right here in our global environment, we could just say data trees, and we can see that we have it, but we don't really need it. We can know it's there because it's built in, but we can do some basic summaries like the dimension function, dim function, which gives you the number of rows and the number of columns. You can learn more about the columns and their numeric type. Each one of these columns represents a vector of numbers, should be all length 31. And we can look at the first few observations. So just kind of things we typically do when we start working with a new data set. We can access each of the columns using the $sign operator, and we can grab those as numeric vectors. And we've all seen all that, but let's get to plotting. So obviously the main plotting function in R is plot, not surprisingly. And if you give plot two numeric vectors, like the girth measurements and the volume measurements, we can, R will automatically know that we want to scatter plot, essentially. So let's run that, see what it looks like. And we see a strong pattern that the trees that are more girthy also have more volume of wood, and that makes sense. Another way to do this would be to let's plot volume And as we start to do statistical analyses, you'll start to see this tilde operator more, this squiggly line. That means it can be read as a function of. So we want to plot volume as a function of girth. And I'm going to say I want to grab the data from the trees data set. And that way I can get the same figure, just a different way to do it. There we go. Just right off the bat, you should know that the plot function has lots and lots of options. So this is a function that has tons of arguments that you can specify to just, tweak every single aspect of this plot and make it look exactly the way you want it to look. If you want to learn about some of those graphical parameters that you can modify within the plot function and all the plotting functions in base R, we do $par. Par stands for graphical parameter. So we can look in the help file for the par function, and we can see that there's lots and lots of parameters you can modify it. Just look at how long this help file is, and it gives you some description of what each of these graphical parameters represents. Let's pick a random one, FG, which I've never used. So again, I don't memorize this. You shouldn't memorize all the graphical parameters. Just know that you can find them and you can manipulate them if you want to. What is FG? It's the color used for the foreground of plots. So you can change the color of the foreground. That's just a random one that I picked that I've never used, but just illustrates how much you can do within the base R plotting function. All right. And we're going to play around with some of the more commonly used graphical parameters, but just know there's way, way more out there. All right. If you want to see what the default graphical parameters are, you can run par with open close parenthesis, and that just gives you all the graphical parameters that R sets by default. But again, you can change all of those. We're going to start off by using the layout function, which is a convenience function that allows us to specify multiple plotting windows side by side, so we can make multi-panel figures and we can compare plots side by side. Because as we've seen, by default there's just one panel, but we can use the layout function and specify multiple panels. And here we're going to specify a 4-panel plotting or graphical device in here. So the layout function requires a matrix, and the matrix will define how we want the plotting panels to be laid out side by side. So let's give it a matrix, and this matrix, as we've already seen, evaluates to this. So we've given it the matrix function, the vector 1, 2, 3, and 4. We've specified the rows and columns, and by default R will fill the matrix in by column. So we have 1, 2, 3, 4. We could alternatively give by row argument equals true, which would make this plotting window look a little different. So the first plot would go in the upper left-hand corner, the second plot would go in the upper right-hand corner, and so on and so forth. By default, you'd have the first plot, in the upper left-hand corner, the second plot in the lower left-hand corner, and you can just specify it the way you want, but this is what we're doing. So I'll get rid of that so this matches what's on the website. And now we have a layout. So you'll see that when we put a plot in, now we have one plot coming up in the upper left-hand corner, and obviously it doesn't look so great. One trick is to hit the zoom button here, and you can see more clearly what's going on. So if you don't like what you're seeing in the plot window and you're trying to fit too much in there, just go into the zoom and you can make this window bigger, and really, or you could even make full screen if you want to really see the plot in a nice big way. So I'll get out of that window, and let's keep filling in this multi-panel figure, and then I'll explain what we did. So let's run this line, which now puts the next plot in the lower left-hand corner because of the way we specified this layout function. Remember what that matrix looks like. So that's the second plot. The third one's going to go up here. And the fourth one will go in the lower right-hand corner. We can zoom in and see what this looks like. And we see that we have this basic scatter plot that we already made in the upper left-hand corner. This one, we have the points are not connected by a solid line. Here we have the points, but we also have lines in between the points. So we both have points and a line. And here the line is connected, whereas here the line is kind of disconnected between the points. So we have multiple ways of visualizing these data. Let's go back and see how we did it. I'm going to get out of that. And so we see that this plot was created just by giving some x values and some y values, and they plot out like as a coordinates on a scatter plot. We use the type argument to specify that we, for this plot here, that we want to make this a line plot. So we say type equals L to connect each point with a line. In this plot, we specify type equals B for both line and point. And for this plot, we specify O for both line and point with connecting lines. So again, lots we can do. Don't memorize any of this, but just know that you can do it. Now, I wouldn't say that any of these figures are publication quality just yet. You might notice a few things that you might want to change. It's probably a good idea just to take a quick look at this and see what you might want to change. Obviously, the axis labels are not good. We can do a better job there. And we probably want to maybe put a plot title potentially. And you can probably think of some other things that are not perfect yet. Let's see, what do we want to do there? So if we make another plot, for instance, on top of this 4-panel layout, you see that the layout is still 4 panels, and then we can fill in the remaining panels with more plots as we go. But sometimes we want to kind of clear that multi-panel device so that we can now have like one big figure again, and we want to make this scatter plot big again, and we can see it. The way to reset the graphical device in R is just to use this graphics off function. Just open close parenthesis, no arguments to the function, but you need to open close parenthesis to specify that it is a function. And that resets the graphical device, and that way when we plot something, it'll be full screen again. All right, let's make another layout, and we can play around with some more graphical parameters here. So here's, we're going to make another layout. This time, the layout is going to be like this. So let's look at the matrix. It's going to be 3 rows, only 1 column of panels. So that's what it should look like. I'll try to make the plotting window as tall as possible, but we may have to use the zoom function to make this look good. But let's run these 3 plot functions. Ha! You can't see it at all, clearly. So we're going to have to use the zoom. So let's zoom in and full screen it and see what we've got here. So the top panel just has solid dots as our points to represent the points. Here we have triangles, and here we have stars. So we're just playing around with the different types of points that we can create, and there's way more than just these 3. Let's see how we did that. We used the PCH argument in the plot function. We specified the character is equal to 19, which just happens to specify a filled point. And the point character, I actually use PCH equals 19 for a lot of my plots. I think that generally looks pretty good. The second, number 2 is an open triangle. I mean, you don't have to memorize, obviously, and there are some great resources online for looking at the different types of point characters. And you can find something like this. This is on the Bootcamp website. And you can see that point character number 2 is a triangle, and 11 is a star, and 19 is an open circle. 20 is a similar, just smaller open circle. So find what you like and use it, and that's all you need to know right now. No memorizing required. Let's do it again. This time we'll use the layout function to specify a bunch of panels, and the matrix will look like this. So again, we have the first plot, second plot, third plot, fourth plot in that order. And let's add the first. Did I run that? Let's make sure I ran that. I'm going to expand the plotting window a little bit and add the first plot. All right. So we have volume versus girth again, but this time we've added a title to the plot. And you'll see the title look better when we use the zoom function, but let's just add the other plots first. This time we're using, for all of these, we're using point PCH equals 19, which is a kind of nice open or closed circle. We're going to specify the x-axis label using the xlab or xlab function. So now we're going to give a more readable x-axis label for tree girth, and we're going to give the units. So let's add the x label. So we're just kind of building up to a more publication quality figure here. Let's see what happens here. We're adding one more element. This is a y-axis label. Again, a more human readable label with our units. And if we want to, we can add this LAS equals 1. Let's look at what it does. You see how the axis label on the Y, you kind of have to tilt your head to one side to actually see it. And here it's readable in the standard reading direction. So that can be useful as well. Let's zoom in and see what we've done. And this is our sort of completed publication quality figure. And it looks pretty good. I mean, you can probably find some things that you'd want to improve there too, but looking pretty good. Let's get out of that and keep on moving. All right. Again, just like always, we're going to create a layout. This time it's going to be a little more sophisticated. Let's look at the matrix that we're using to specify the panel layout in our graphics window. Note that we have 1, 1, 2, 3. This means that the first figure is going to take up the entire left-hand side, whereas the second plot that we add to this graphics device is going to be in the upper right-hand corner, and the third is going to be in the lower right-hand corner. So we can do a lot more sophisticated things with the layout function than you might think. It's pretty sophisticated. Again, you can make almost any figure if you know enough, and it's not that hard because there's lots of great code out there, lots of code you can borrow. You can do almost anything with base R graphics. All right. So let's run that layout function, and this time we're going to add some more detail to this plot. So let's do that. First, let's run this. So again, this entire plot is going to fill up the left-hand side. What have we done? We've added a color. So the color argument is just COL, and you can specify a whole number of different colors. We're specifying a blue color. We can specify whatever we want. So if we wanted to specify red, we could. Let's just recreate the layout and go back to blue. So here we go. There we go. That's where we were. And let's see what happens if we add multiple colors. So now we're going to add black and blue. Always great color combination right there. So let's see what happens. Well, R is going to do that recycling thing it does because it knows it has like 31 different points, and yet we've only specified 2 colors here, black and blue, so it's just going to be black, blue, black, blue, black, blue, all the way to 31. It's just going to recycle that vector of colors. you could, if you wanted to, give it an entire vector of 32 colors, and every color would correspond to a particular point. So we could do that if we wanted to. Let's see what this last one does. So you see what we did? It's blue. They're all blue, but they vary. The points vary in terms of the character or the plotting symbol. And we're varying between plotting symbol 1 and plotting symbol 19. 1 is an open circle and 19 is a closed circle. And so again, R is just recycling for every one of our trees, our observations. It's going to recycle between open, closed, open, closed, open, closed, and give us something that like this. And we can zoom in to see this in more detail. All right, just open and closed points here. All right, let's graduate to a different data set. So we're going to use the iris data set. This is from it's a very commonly used example. You can read more about this. Sometimes it's called the Fisher's iris data set. Sometimes it's called the Anderson's iris data set. And it gives you measurements or flower measurements for iris individuals of 3 different species. We have 50 flowers from each of 3 species of iris, and therefore there's 150 rows in this data set. And we have 5 different measurements: sepal length, sepal width, petal length, petal width, and the species. So let's look at that should be what we have. So we have 1, 2, 3, 4, 5 columns, and how many rows do we have? 150 rows, 5 columns. We can learn a little more. So again, it's a data set you'll probably see. If you haven't already seen it in a stats class, you will probably see it because it's used in pretty much every stats class that deals with like classification and multivariate. So you will see that. And what we're going to try to do here is to color each of the observations. We're going to make a scatter plot just like before, but we're going to color observations to specify which of the 3 iris species each observation belongs to. So we're going to make a vector of colors. The colors will represent the different species. And now we're going to take each of these colors and repeat them 50 times. So we're going to use the rep, which you may recall from one of our earlier videos. We're going to take this plot color vector, which is just violet, purple, blue, and we're going to replicate each of those 50 times. So we're going to make a vector that looks like this, which is now of length 150, which is the same length as our iris data set. Why did we do this? Well, let's look more closely at the iris data set. If you look at the species, you'll see that actually the first 50 observations are all one species, the second 50 observations are all another species, and the third 50 observations are another species. So if we know that the data set is structured that way, we can create a vector of colors where the first 50 colors are all one, the second 50 colors are all another, and that's going to correspond to species because we know that based on this species vector. So here's our, oops, I never actually ran the color vector. This is our vector of colors that we can add to our plotting call. And before we actually do this, let's just plot the petal length. Actually, I'll plot sepal length as a function of petal length. So sepal length is going to be on the y, and petal length is going to be on the x, and I have to give it the iris data. Let's just see what the base, actually, let's get rid of our panels for now and plot that again so we can see it more clearly. And we have sepal length and petal length, and clearly there's a relationship, but there's also some other stuff going on because there's a bunch of observations clustered over here and then the rest of them over here. So that may be related to species, but we can't see that on this figure. So what we're going to try to do is color the observations by species so that we have a better idea of what's really happening in this figure. So let's look at that. So what we're going to do is we're going to give here just another way of specifying what's on the x and y axis, but the x is the petal length, the y axis is sepal length. We're going to make the point character 19, so we have filled circles, and let's just look more carefully. So the color is going to be this color vector, and so we're basically going to specify the color of every single observation, and it's going to be colored by species. And we're going to give a main plot title as well. So let's do that. I'll give it a little more space so we can see this more clearly. And there we go. So it already looks kind of cool. I don't know if those colors are the best for visually, but we do see that this is one color, this is one color, and this is one color. So the species do kind of like separate out. So this gives us a lot more information than we had in our previous figure that didn't have any colors. Plus we have nice labels now. Well, we don't have good axis labels here, but at least we have a plot title. So we can do a lot better, and we will. But this is a good start. So let's take our plot colors, and first we're going to label them so that we have a named vector, and this can help us keep things straight here. So we have now violet is going to be setosa, that's the first 50. Purple is going to be versicolor, that's the second 50 observations, and then Iris virginica is going to be blue, and that's the third. So here we have setosa, versicolor, virginica. Obviously, we're going to want to put a legend on this figure. Otherwise, the information, the colors are there, but you have no idea what the colors mean. So you need a legend when you start to add things like color into figures. So let's make this figure look a little better given what we already know about plotting before we move on in the script, because the next portion of the script here is a little bit of an aside about programming, but we'll get to that in just a second. So first of all, let's copy what we have up here, which generated a nice but incomplete figure, and add some more elements to it. So let's add a x-axis label. We can just call it petal length, and I'm not going to put units on yet, but you could, and I'll put a y-axis label, and that's going to be sepal length. So if we run that, it looks better, but we still don't have that legend, and we can add a legend. We'll go through this in a little more detail in a second, but you use the legend function. You specify where you want the legend to go. I'm going to put it in the top left, and you specify the different aspects of the legend that you want to, in this case the color is communicating information, so you need to change the color. So I'm going to say color equals plot colors, and so this specifies colors that R recognizes, so that we're going to basically have 3 different colors. Since these are points, we're going to specify the point character equals 19. Since I just say 19, it'll know that that's for all 3 species. And then I have to name the species. So we give the legend, which here is specifying what the labels are going to be in the legend, and that's going to be the same thing as the names of the plot colors, since we already named it. And there's a couple other things we can do to make things look better. I can, by default, it's going to be like a box around the legend, but I can say I don't want a box, and now we have a legend. Don't worry, I went through that really fast, but we'll go through legends in a second. So now we have a much more nice publication quality figure, which means we can now move on to our aside about programming. So remember what we did to specify the colors for every observation. We had to know that the species in the iris data set is organized in a very specific way, where you have 50 observations of one species followed by 50 observations of another and another. And so we used this lazy technique of matching species with color by just simply replicating each of 3 different colors 50 times. And we could only do that with this case. That is not a general technique. Now in programming, we often want to build general code that could work with other data sets. There's a bunch of reasons for that, but one is that it is foolproof. Now, if we accidentally sorted this data set in a different way that's not 50 species of species 1, 50 of species 2, but it's sorted by something else that mixes up the species, this code is not going to work anymore. And we're basically going to break the code, or we're going to give erroneous results. If we code it in a way that's foolproof or fail-safe, no matter how the species are coded, we're still going to have the species linked properly to a color. And so this figure will look good regardless of how we sort the data set. So let's look at this. So what we're going to use here is we're going to build a fail-safe method. And now there's multiple ways to do this, like always with programming. But here we can use the match function. And the match function goes through each element of one vector and finds the matching index in the second vector. So here, and don't worry, it takes a while to really master the match function. But let's just look at what it's doing. So first we're going to give the match function the species list, which here is ordered 50, 50, 50, but it doesn't have to be. And we're going to give it the names of the plot colors, which should match with the species names. And so what it's going to do is it's going to take this first observation here and say, okay, which of this vector, what index does that correspond to? Well, it corresponds to 1. So that's going to come back with 1 in the match function. And all of the first 50 is going to be 1. Second 50 is going to be 2 because that's the second index of the plot colors. And all the last ones are going to be 3 because they're the third index. So it's going to look like 1, 1, 1, 1, 1, 50 times, 2, 2, 2, 2, 2, 50 times, and so on and so forth. And we can see that. That's what it looks like. And that's great, but the thing about this is it's fail-safe. Even if the colors were mixed up, we'd still have them properly matched to the species. So, and we'll show that in a second. But first let's store that, the results from the match function right here as a variable in our workspace called indices. There we go. And now if we want to make a color vector, we just take the plot colors, remember it looks like this, and we use the indices that we just created to generate a vector of length 150, because this index vector is length 150. So when we do this, we're going to basically repeat. Here we're giving this index, this indices variable here as we're kind of subsetting this vector. The plot colors vector is only length 3, but since we're giving it since we're indexing it with 1, 1, 1, 1, 1, we're basically repeating violet, 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 violet over and over again, and then we're repeating purple, 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 purple over again. So we're basically recreating that color vector. If we run that line, we'll have a bunch of violets, a bunch of purples, and a bunch of blues, right? So that's nice. That's basically the same color vector we created before, but this time it's fail-safe. And so we could rerun the code with this new color vector 2, and to get the same results, right? But let's now make a version of the iris data frame that's not in order anymore. So I'm just going to reorder the iris data. In fact, I'm using a random function, so whatever my results are probably not going to match yours, but I'm just giving you an example of using the sample function to generate random integers between 1 and the total number of rows. So this is a common technique for bootstrapping in statistics if you ever get around to that. But you can see what the sample function generates. It just generates a bunch of indices between 1 and the length of the iris data set in terms of the number of rows. So we're just going to be able to basically create a bootstrapped iris data set that is certainly not organized by species anymore. It's just randomly scrambled up. And we're going to call that iris 2, So let's run that and look at iris 2, and you can see that the species are all scrambled up. So how do we visualize this data set where in a very similar visualization where we want to separate species by color? Obviously, we can't just say the first 50 observations are one species and so on and so forth. That won't work. So let's repeat those steps. We're going to make a bunch of a vector of indices using the match function. So that's going to explicitly match the species with a color. And you'll see now that it's not 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3. It's all mixed up, but they should be matched. The species and the colors should match. We'll create the color vector the same way we did before by using these indices to, again, match colors to species. And here, all Virginica should be blue. Even though they're not in the right order, every time you see Virginica, you should see blue. Every time you see Versicolor, you should see purple. We have a fail-safe now. We mix things up, but it still works, and we'll still get something that looks similar where the species are properly mixed, or they're properly identified by color. The old method, if we wanted to repeat the colors each 50 times, is going to result in a complete mixing up of colors. So there's no information content in the colors. The color means nothing in this figure. All right, so let's add a legend. We'll play around with the legend function in more detail, but this time we're going to make multiple panels so we can see some different legend characteristics. So here we go. And of course, if you want to uncomment this or just learn more about how to make legends, you can. But let's just look at this. So we'll first set the layout so we have 3 plots, one on top. Oh no, we're going to make them next to each other. So look at the matrix that we're going to use here. So now we'll have 3 plots side by side, and the first plot, so I'm going to make even more space here so we can have these plots side by side and make it look nice. And we're going to make a plot, and the plot looks good. It has the right colors. It has good axis labels and everything. Let's add a legend. This one has a box around it. We'll make a similar plot and add a legend. This one omits the box. And here, we're going to add a third legend. It doesn't have a box, and the text is properly italicized to represent scientific names. So let's zoom in there and just see how beautiful it looks. There we go. So this one's pretty much ready to go. Publication quality figure, although my face is over it. So what we could do is just make it a little bigger like this. And there we go. So anyway, whatever. You can see this looks pretty good. So now let's just look at how we did the legends in each of these 3. So the first one, just use the legend function. You give it the location of the legend in the top left. The point character is 19 for all 3. The color is the plot colors. The legend is the species names. And we give the box type of no, or the box type, or if we don't specify BTY is no, then we get a box, which I think kind of looks ugly. So I don't like that box. So this box here, that is. And so yeah, not a big fan of the box. This first legend also doesn't have the correct scientific notation. It doesn't have the genus ID. So we're just kind of building up complexity. But this final legend is the one that has all the bells and whistles. We get rid of the box. We say text font equals 3, which means italicize, and we give the proper scientific names. So again, there's a lot more to learn, but hopefully this will get you started. All right, let's dive into a different data set, and we'll learn a few more graphical tricks. This time we're going to use the built-in motor trend cars or MT cars data. We've seen this briefly before, but if you want to learn more, use the help function. We can look at the data, we could do summaries just like we always do. And here's the first few rows of the MT cars data. We'll see that there's fuel economy, and there's a whole bunch of other parameters that are related to the car weight, the car displacement, and the cylinders, and all these other car things that I don't really know very well, but here they are. Let's do a couple plots, and before we do that, we remember that the plotting window has a bunch of panels, so let's first get rid of those. We'll do graphics off and shut down, and we will reset the graphics device so that all the defaults are there, so we can now plot so that we just have a single scatter plot. So here we have fuel economy as a function of vehicle weight. You can see that tilde. So we're plotting this on the y-axis, this on the x-axis. We're pulling the data from MT cars, so these should be column names in MT cars. We're using the point 20, which is a smaller closed circle. We're giving proper axis labels, so it already looks pretty good. But what if we want to include some more information in there? We might want to include information on horsepower, for instance. So we have horsepower here. So we might have a hypothesis that, yeah, as the vehicle weight goes up, the fuel economy is going down, but horsepower, for a given weight, vehicles with more horsepower should be have lower fuel economy, and higher horsepower should have lower fuel economy. So we want to incorporate additional information on horsepower into this figure. How can we do that? Horsepower is a quantitative variable. So if we look at MT cars, horsepower, HP, you see it's a quantitative variable. How do we code this in? We could do it by some sort of a continuous color ramp. We could do it by the size of the character. Like we could make bigger points for cars that have more horsepower, and we can make smaller points for, so we could just use the size of the points to indicate horsepower. So we can try both of those things, and I would recommend trying different things and seeing what you think looks best. Sometimes you don't know until you try it. First, we have to take the horsepower and scale it in a way that, if we're going to change the size, we can't necessarily have one of these points be size 200 because it'll take up the whole figure. So we have to kind of rescale the horsepower variable so that it's a manageable range of sizes. So one way to do that is just to scale the size from 0 to 1, or scale the horsepower, from 0 to 1. To do that, we're going to use this width function, and width is a safer way to attach a data frame. So basically we're saying we're going to take this data frame. With that data frame, we're going to take the column that represents that is called HP, and we're going to basically not have to keep referencing the MT cars data set. We're just going to say, with this data set, we're going to do this calculation with the column named HP. So we're just kind of, don't worry too much if you don't get that, but it's just avoiding me having to retype MT cars over and over and over again. In fact, it could be instructive to just show you what's going on here. So I'll pull this out and get rid of these. So what I'm saying here, what did I do? Okay. You see that if I run this as is, R doesn't know where, because HP isn't an object in my global environment, so I can't use HP. So I would have to say MT cars $HP and just do that over and over and over again to do this. Now I think I screwed something up because really need to do to scale it between 0 and 1 is to do something like that. So I was just off with parentheses, but what the point is that there is no HP object in here. So to reference horsepower, I have to reference the MT cars data set, so it gets a little cumbersome. If I use the with function, I can just specify MT cars once, and then it knows that I'm in the MT cars data set, and it will recognize objects that are columns in that data. So it'll recognize information that's in that data set, like HP. So now I can run the same rescale operation, but only have to specify MT cars once, and I get the same results, as you can see here. So it's just kind of a convenience thing. It's good to know because you will see that frequently when you get sample code from places. All right, let's do a plot, but this time what we're going to do is try to code the point size according to the horsepower, and we're going to use this HP rescale, but I am going to, and I did this by trial and error, just sort of played around with values that kind of changed the overall size to make things look good. And so I added 0.6 to the HP rescale, and then I multiplied all of that by 1.2, and that just made it look good. So that was just trial and error. So let's see what that looks like. And we can zoom in and see that we have now represented horsepower as the size of the open circles. And overall, you can see that for a given for a given vehicle weight, the more horsepower, the lower fuel economy. So you have a really high fuel economy car that's the same weight as a lower fuel economy car, and the difference here is that this one is higher horsepower. So we're now visualizing, we're adding a lot of new information to our figure, which is kind of cool. Of course, we'd want to add a legend and specify that, at least put a couple different levels. That doesn't look great, but we can make it look better. I'm not going to worry too much because this is just a demo, but let's, I think it's going to look better now. All right. But either way, trial and error is a good thing. And so here's one way to represent the information we're trying to represent. Fuel economy as a function of weight, but also horsepower. All right. Now we could do the same thing, but instead use colors. We'll make a color ramp with 125 different colors that vary from, colors typically used to represent low elevation terrain and colors typically used to represent high elevation terrain. And these hexadecimal things are just representing colors for R's purposes. So what I'm going to do is to recode the horsepower in a way that connects it with this color ramp. I'm going to take the HP rescale and rescale it again, essentially, to represent a range of colors from around 1 to 100 and whatever it is, 100 and around 100. So now, colors that are lower, that have lower indices, or observations with lower indices represent are going to look more like low terrain colors, and observations with high horsepower are going to be represented by colors that with higher terrain that represent, or typically used to represent high elevation terrain. So now we have a bunch of indices, and we can now plot different colors that represent different horsepowers. And if we include a legend, we can see that the greens typically represent lower elevations, kind of valleys, and so that's going to be lower horsepower, and you have more icy towards like white conditions that represent high horsepower. This may not be a great way to do it, but again, just play around with it, find something that looks right. This is just illustrating that you can code additional information into your figures using color or using the size of your characters and so on and so forth. So hopefully that didn't confuse you too much. I just want to give you some tools. Of course, you're going to want to go out and just try things, make mistakes, just use trial and error and find something that works for you. All right, before we end the plotting session, I just wanted to go through a bar plot example. Now, bar plots aren't always the best way to visualize things, but this still illustrates some useful concepts. So first thing I'm going to do is to specify the bar heights. And so what I'm going to try to do is represent the sepal length as a function of species. So I'm going to have 3 different bars, and the y-axis is going to represent the mean sepal length. So I'm going to use this thing called tapply, which is, and I'm starting to go faster, and you don't feel like you have to memorize any of this, but what tapply is going to do is it's going to take this sepal length, which is again 150 elements vector, and it's going to first summarize them by species, and then it's going to take the mean. So it's going to take sepal length, it's going to summarize them by species, and it's going to take the mean for each species. And so what we end up with is a mean sepal length for Iris setosa, a mean sepal length for versicolor, and a mean for virginica. And those are what we can use to plot, as a bar plot. We'll plot the means. So first, let's store the bar heights as a variable in our workspace. And let's make a bar plot. So the bar plot is just going to look pretty plain here, but it's going to give the mean sepal length for each species visualized as a bar plot. We can add some flair, obviously, like we can always do with the plot function or any derivative of the plot function, like the bar plot function. Many of the graphical parameters will remain exactly the same. So we can specify the name. We can give a title to our plot. We can specify Y labels. We can specify the names of each of these species, and we'll do it in a way that's more scientifically rigorous. So we'll give it I setosa, I versicolor, and so on and so forth. We'll give LAS equals 1, which will reverse the y-axis so you don't have to twist your neck. And we'll, just for fun, we'll give it some different colors for each species. So let's run that. And the colors are obviously totally gratuitous. There's no reason to use color here, but that's what we're doing. And this is what the plot ends up looking like. All right. Of course, we're not done, because if you want to plot out the mean, you should probably also put some kind of error bars on this bar plot to indicate how variable the sepal length is. We know the mean, but let's see how variable it is. So we can do something similar to the tapply function, but we could use, in fact, we could use tapply, and let's just we'll show you that. To calculate the standard deviation of sepal length for each species. So again, we're going to put sepal length in there. All right. So we're going to take the sepal length. We're going to summarize by species. And the way we're going to summarize instead of the mean is by using the standard deviation, which in R is specified as SD. And here you can get the standard deviations. So if we're going to make error bars, we might want to put one standard deviation on each side of these bars to represent the variability of each of these species in terms of sepal length. Another way to do it is to use the by function, which is just it's a same thing as tapply. We're going to take the sepal length, we're going to summarize by species, and the summary statistic is going to be standard deviation. So and the error bars are going to be 2 standard deviations on either side. So we're going to multiply that by 2. And so our numbers are going to look like this. The by function does do something a little bit different here, but this is twice the standard deviation. So 0.352 times 2 is 0.7. So there's twice the standard deviation. This is twice the standard deviation for versicolor, and this is twice the standard deviation for virginica. And we're going to make the lower bounds be the mean sepal length minus the confidence, minus 2 times the standard deviation, and the upper bound of the error bar is going to be the mean plus 2 standard deviations. All right, so we're going to set the lower bounds for our error bars. We're going to set the upper bounds for the error bars. And we can make the bar plot, but I'm going to add a little extra space. So I'm adding this y-lim argument, which just expands the y-axis a little bit to allow for the addition of the error bars. Otherwise, everything else is the same. I have these gratuitous colors in there for no reason, but also have proper names for the bars and so on and so forth. One thing I did was to assign the results of bar plot to an object. And the reason I do that is because if I'm going to add error bars to this bar plot, I need to know where the center of each bar is on the x-axis. Clearly, the x-axis is not quantitative. Like these are just qualitative labels. It's hard to know, is this 1? Is this 2? Is this 3? By default, if you assign the results of bar plot to an object, it gives you the center. It gives you the x coordinate of the center of each bar. And so if I do that, I'll see that the center of this is 0.7. I would never have been able to guess that. The center here is 1.9 and 3.1. So if we want to add elements to our plot, it's really important to know where the center is so we can add this confidence bars or error bars onto our plot in this case. So to do that, we use the arrows function, which allows us to add error bars onto a bar plot. What we do is we give the starting coordinates of each of the arrows. So the starting coordinate are going to be these, so the x coordinate is always going to be the center. So we want the lower bound and the upper bound to be right on the center of this bar, same here and same here. And the y values are going to be the starting point of the arrow. It doesn't matter which one is starting and which is ending, but one end of the y-axis is going to be the lower bound, and the other end of the y-axis is going to be the upper bounds. When I say code equals 3, honestly, I kind of forget what code equals 3 is, so let's look up the arrows function and see what code means. So code gives the kind of arrows to be drawn. Code equals 1 is an arrowhead drawn at the beginning of each arrow. The code equals 2 is the arrowhead drawn on the other side. Code equals 3 means a head drawn on both sides, and that does make sense here because we want a kind of tick mark on both sides of the error bars. So that's why we say code equals 3. Angle equals 90 just means that we're not going to have arrows like this. We're going to have just tick marks at each end of the arrow. and this specifies the length of the tick mark. So again, you can play around with these things, but let's go back to the plot window and add the error bars. So there we go. They're right at the center of each bar, and they have appropriate tick marks, and that represents 2 standard deviations on either side of the mean. All right. Pretty much the last thing I want to mention is histograms, which are a super useful way to visualize or summarize data that we're working with. So again, we're sticking with the iris data set for now, but let's make our layout. We'll add a 2-panel layout, and we'll make a couple histograms. So the histograms are made with the hist function. If you just make a standard histogram, you could just do hist and just put in any vector that's a quantitative. So we'll say iris sepal length, and we can just make a histogram of sepal length here, and it just gives you, it kind of puts the sepal length into some bins and specifies the frequency of observations occurring with each of those bins. So we have some 20-something observations that have sepal length between 4.5 and 5, for instance. And so it's just a good way to summarize where the majority of the data lie, and if there are any outliers that are like way outside the range of most of the other data. So a good visualization tool, and just like any other plotting function, we can add, so here I'll recreate this. So we can add the plot title, we can add names to the x-axis and the y-axis if we want. All or most of the plotting parameters are there for you if you want to make it look better. And one thing we can do with histograms is change the y-axis from just the frequency of occurrence in each bin to the probability density of occurrence within each bin. So here we go. So now we have the same figure, but now it's in terms of probability density. Why is this useful? Well, that means we can overlay some probability distributions if we want. So if we wanted to do a kernel density distribution and just see kind of a continuous probability distribution across the range of sepal length, that the highest probability density, the most likely values are between 5 and 7, but going down to 8 or so. But we could also plot a known probability distribution, like a normal distribution, a Gaussian distribution on top of this. So I will put a Gaussian distribution on top with a mean of the mean sepal length in the data set and a standard deviation equal to the standard deviation of sepal length in the data set. And I'm just going to say add equals true to add this normal distribution on top of an existing figure. It's going to be this. This is our active plotting window. I will make this a red line illustrating a normal distribution, and I'll make it thick by saying, or no, I'll make it a dotted or dotted dashed line using line type equals 3. Note that we're using the curve function here to add the normal distribution on top of this active plot that we're working with. And the curve function, you don't have to know much about it, but what it's doing, it's a convenience function for plotting the results of a function across a specified range. Don't worry too much about it. You can look up other examples, but what we're doing is we're just adding a normal distribution on top of this. If we wanted to even do a better job of that, it looks like we'd probably have to add a little more space to our y-axis. So we could go back here and make the limits of the y-axis a little bigger. So I'll make it from 0 to 0.6, for instance. And let me just get rid of the graphics. We'll just do a single plot, and we'll add a little more space in the y-axis, and I'll omit the kernel density, and I'll just add the normal distribution. In fact, I'll add another parameter to make the line thicker. So line width, equals 2, well, not 23, 2. That'll make it nice and wide, and we can add a normal distribution on top of it, so we can see how well the distribution of sepal lengths matches a normal distribution. We're not doing any tests here, but it's kind of nice to see, to overlay these two. And sometimes if there's an assumption of normality, this is a really good way to visualize that. Okay, very last thing. There's a useful function called pairs, which allows us to look at relationships among all the different variables in a data set. And so if we do that with Iris, it automatically gives us, and we saw this way back at the Whirlwind tour, but we can see how, say, petal length looks versus sepal width, and so on and so forth. It's just with one fell swoop, one quick call to the pairs function, you can get a lot of information. Good way to explore any possible relationships in your data set. All right, we've reached the end of the plotting portion. So if you go back to the plotting, or go back to Bootcamp 1, Module 3, and go to where it says challenge yourself by recreating the following plots. Do that now. Challenge yourself and see if you can accomplish what you're asked to do in the challenge problems here. And in the next video, we will go over some very basic statistics, and I will see you then.